invitation and the introduction. So I will be talking about sustainably synthesized metal organic frameworks for sustainability applications, about the activities of my groups, and this is really not as Bernard already mentioned. There is more going on, but I'm just trying to capture a little bit a sense of it. So we're looking at mostly metal organic frameworks, and I will give a more detailed introduction of what they are, but at the moment, I would just like to emphasize that they're porous crystalline materials, and we're really interested in adding guest materials and particles inside, and look at the interface between the guest and the host framework, and try to kind of use tune the interactions between them to, in particular, to tune the properties of the guest material. And I will also talk some examples, but here some examples in this vein. But we at the moment have three, well, sort of larger projects ongoing. One of them is focused on embedding nanoparticles and nanoclusters inside the pores of frameworks and look at their catalytic properties. So from a sustainability viewpoint, that can be, for example, for fuel synthesis, but it's obviously not restricted to that. We're also looking at the fabrication of membranes for applications in fuel cells. So in my talk, I will be talking about more about these two possible applications. But we're also looking at these frameworks as solid-state electrolytes, for example, for all solid-state lithium-ion batteries, in which the channels of the frameworks allow it kind of like a highway for the ion transport. And of course, we are trying to make these frameworks in a sustainable fashion. And if time permits, I will give a couple of examples of that as well. So just a couple of words of the Queen Mary University of London. So it's one of the few Russell Group universities in the UK. And this is sort of a semi-campus-based university in central London. So we're in the East End. This is really our most, well, our prettiest buildings, really, but no, they don't like this. And as you can see, the weather is absolutely wonderful, and we've got palm trees and everything. So just a bit of the structure of my talk. So I'd like to put it as this way, closing the loop, because we're, as I mentioned, we're looking at closing the loop in terms of our energy use and generation and conversion. And also we're looking at closing the materials loop, and I will elaborate a little bit on that later. And as I already mentioned, we're working mostly with metal organic frameworks, so I'm sure that most of you are familiar with this class of materials, but I will give just a little brief introduction to those who have not come across them just yet. And the few examples of our research, really just a little bit of a taste I will give on catalysis and on hydroxide ion conducting membranes and sustainable synthesis of metal organic frameworks. So the first question, or the first point, is really the closing the energy loop, or shifting the energy paradigm, if I to get some sort of more cliches. And so you would be familiar with the carbon cycle that nature provides us. So through photosynthesis, plants are able to bind and capture carbon, which then can be converted into biomass. And in a reductive atmosphere, or reducing atmosphere, this can be converted into fossil fuels, which of course we have been using so far as our primary energy carriers. So of course, when we combust fossil fuels, they generate carbon dioxide, and in principle that can be recaptured through the process of photosynthesis as well. But obviously the issue is the time scale of these processes. So while the combustion, of course, of biomass or in the fossil fuels is a very quick process, it's capture, photosynthesis, and further conversion into more reduced forms of carbon takes millions and millions of years. So if you're looking at our current energy use and using fossil fuels as energy carriers, if you want to look at it, you can kind of view this as nature has provided us with the loop, and humanity found a way to hack it. And this is what we're doing. And ideally, of course, what we would want is to find a more sustainable way in both senses. So on the one hand, of course, one that does not rely on slower processes and more limited processes, but also it's of course the time scale adjustment that is needed. And of course, what we would want is to really scale up the energy storage system to our needs, not just in terms of the time scale of the processes, but also in terms of the storage capacity. And so we've got several ways of doing it. I'm sure you'd be familiar with this, but and particularly with the concept of energy storage. And we're always relying or trying to rely on this kind of loop. So we can look at batteries, for example, in which case, of course, the renewable energy sources are linked up with the storage system. We can also look at synthetic fuels, so one example, but this of course doesn't have to, it's not the unique example we can use, but of course we can similarly to nature capture carbon dioxide and reduce it into synthetic fuels, which would be a carbon neutral alternative. And another synthetic fuel we can look at is hydrogen, in which case, for example, we can use solar energy to split water into hydrogen and oxygen, store hydrogen, and then use these fuel cells for the controlled oxidation of hydrogen into water. So some examples I would be given would be perhaps related to these two, but not necessarily in these forms. New materials and high performance materials developed to convert one type of energy into another type of energy, as well as for storage systems. So regardless if you're going with battery technology, so electrochemical energy storage, or with synthetic fuels, so chemical energy storage, we will always need materials. So, of course, when we do using materials, we need to mine them, we need to transform them into a form that we can use, and obviously we would want them to be robust, but every single product will reach its end of time, at which point it shouldn't be ideally discarded. It could be recyclable or even upcyclable. So we also need to consider the materials loop. We need to use materials that can be obtained in sort of a greener and sustainable fashion, and also ideally can be given a second and third and fourth life and so on. So that is what I mean by shifting the materials paradigm. So my group is mostly working with metal organic frameworks. I'll just sometimes call them as MOF. I think nowadays they're fairly well-known materials, so they've been around for 20, 25 years. What I would like to say that for me, they're very interesting because they're almost nothing. So what they're made up of is they're kind of hybrid material made up of inorganic and organic building blocks. So these are sort of inorganic nodes that are interconnected by organic linkers. And so these inorganic nodes can be either cations or some metal oxide clusters. And when they self-assemble, they form these typically crystalline and highly porous frameworks. And that's why I'm saying that it's almost nothing, because what I'm really interested in is what's in the cavity, really. So it's on the interface, that's not the material itself. Now, it's, and I mentioned briefly that my group is really interested in sort of adding guest materials and looking at the interaction between the guest materials and the host framework. So everything that happens here on the wall of these pores and in the interface is of great interest. Now, that of course is important to know that that there are two main things that will influence that. On the one hand, it's the chemistry of these pores. On the other hand is the geometry of these pores, and particularly because, and I should also mention, is that the size of these pores, because they're in the very, very small end of the nanometer scale. So they're typically between 0.3 to 3 nanometers. Yeah, so it's almost like beyond the nanoscale, if you wish. So when I'm talking about geometry as one important thing, again, and perhaps unrivaled properties of metal organic frameworks, is that we can have an absolutely huge number of possible pore sizes and shapes. And what's important to point out, when I mentioned how they're built up of these building blocks, is that the pores that are in the frames are part of the crystal structure. So they're very well determined in terms of shapes and size, and they are the same throughout the crystal structure. So that is important. And of course, if we consider what they're made of, so this is the inorganic wood, so this could be typically transition metal cations or metal oxide clusters, or the organic linkers can be polycarboxylates or heteroaromatic systems. So from inorganic and organic chemistry, we know that there is a lot of options for these. And of course, the shape and the size of the pores depends on the valency and the nature, the chemistry, if you wish, of these building blocks. So there is a huge amount of pores, shapes and sizes accessible to us. So these are just a few of these. And of course, we can put all sorts of chemical functionalities onto the organic group, so we can tune the geometry and we can tune the chemistry. I think I've come a long way to say this very simple thing. So we can have many different types of pores and very different types of wall chemistry. And of course, in order to tune that host-guest interaction, these are the things that matter. So this would have been my introduction, and I would like to give just a few examples of the applications we're looking at, and I will start with sustainability applications. In particular, we start with the catalysis part. And the reaction I will be talking about is a hydrogenation reaction. This is not the only type of reactions we're looking at, but in my view, this represents quite nicely the advantage of this kind of materials that we can have. And so here what we will be looking at is the combination of palladium. So what we would want is really to take a pore space to embed a palladium particle and use this composite as the catalyst itself. Now, why palladium? Palladium is known to be a quite good catalyst for hydrogenation reactions. And one thing is, and I'm sure that Bernard and of course Herman will be quite familiar with this, that when palladium is exposed to hydrogen, it does react with it. So it's not just the reaction that would happen on the surface, which you would expect from platinum, for example, that when it's exposed to hydrogen pressure, then hydrogen molecules would chemisol on the surface and split into atoms. In the case of palladium, what may happen is that, and what it does happen in quite a broad range of conditions, is that the so split hydrogen atoms may diffuse inside of the palladium metal into the bulk, And as long as the hydrogen concentration is low enough, that would not necessarily be an issue or a challenge or an opportunity, depending on the angle you're looking at. So it would form a kind of a solid solution phase with palladium metal, whose properties would be essentially the same as that of the metal. Now, when we're increasing the hydrogen concentration or the hydrogen pressure at any given condition, what would happen is that at some point, the concentration of the hydrogen dispersed within the metallic phase would be high enough for it to penetrate and occupy the interstitial positions within the palladium lattice. And that is called the beta phase. Now, this is very important because once this phase forms, the properties of this material, this hydride, will be very different from the metal. So at the moment, I'm talking about the physical properties. So for example, they're no longer metallic. So obviously the color of them would be different. So they wouldn't be gray and shiny. And also the optoelectronic and electric properties would be different. So it would no longer be a conductor either. And so for this type of hydride, this interstitial hydride for palladium, forms at relatively broad range of hydrogen pressures and temperature intervals as well. And that is important because obviously it also forms in the conditions that are industrially relevant for catalytic applications. So to come back to hydrogenation reactions and as catalyzed by palladium, of course, because of this phenomenon, they would be slightly different, because the question would arise if it's the metallic phase that is catalytically active, or it's the hydride phase that is catalytically active, and whether or not we can tune the catalyst to only produce one type of this species in the course of the reaction. So that is a little bit of the introduction why palladium, why we chose this hydrogenation reaction to look at. And so one more thing that we need to consider, and this is very simplistic in a way, but I just want to capture the essence of what else needs to be considered when we want to look at it. And of course, there are some conditions that need to be fulfilled in order to control whether or not the hydride phase or this interstitial hydride phase in palladium may form. And one of this is the particle size. So we have seen that for the interstitial hydride, obviously you need interstices for the hydrogen atoms to be taken up. So if we don't have a bulk of palladium, we won't have a hydride phase either. And I'm sure that you're familiar with the idea of increased surface to volume ratio as we make particles smaller and smaller. But just to show you an example, so here we have a 0.8 nanometer sized metal cluster, and it has 18 atoms, which means that there is only one atom in the middle and 17 atoms are on the surface. So that means that practically, so in a practical sense, there is no interstices in this particle, because it's simply too small for those interatomic or intermetal atomic spaces to be around for the hydrogen to occupy. Now, the other thing, and then I forgot to mention it in my short introduction of the formation of hydride phase, or the interstitial hydride phase, that this formation of the hydride phase, the occupation of the interstices by the hydrogen atom, it also is accompanied by a tangible expansion of the volume. Now, if we have a particle that is really confined physically and spatially in a space that is not free to expand, of course, the hydride phase once again will not form. So in order for us to determine whether or not it's the hydride phase that's active or it's the metallic phase that is active, we can come to a situation or find a system in which we know that the hydride phase is unlikely to form, and try to compare that with other systems in which it may form, and see whether or not we can draw any conclusions with respect to the catalytic properties of the palladium particles. So we have previously, for completely different purposes, looked at the system in which we use the UIO66 topology. So this is what it looks like. It's one of the archetypal metal organic framework topologies with zirconia-like clusters interconnected by terephthalic acid linkers. And we noticed that in the case we use the aminoterephthalate linker, we managed to confine and grow palladium nanoclusters inside the pores of the framework. So this is AADF STM micrograph of the palladium amino UIO66. And you can see that we have well dispersed palladium particles. So they are the bright spots of sizes either 7 or 11 angstroms. So this is a very good agreement with the pore sizes of the framework. So we knew that these are very tiny. And if you perhaps recall those clusters I was showing, so if we had a particle of 0.8 nanometers, we only had 18 atoms in that. So perhaps we thought that might be a good model system in which we don't have a lot of interstices, and perhaps we can't form the hydride phase. So the reaction we decided to look at is the selective hydrogenation of 1,3-butadiene. And so this is the reaction we ideally would like to carry out. So we have 2 double bonds, and we would ideally only like to hydrogenate one of those. Now, hydrogen is a known catalyst for this, and this is also an industrially relevant reaction. So this is kind of a good model system for us. However, there is a problem of overhydrogenation in which we get from the butadiene to the butane rather than to the butene. And of course, this is something that we would like to avoid. Now also, and I just put it there in advance, that it previously has been hypothesized that this might be a consequence of the presence of the hydride phase. So we were wondering if we can inhibit the formation of the hydride phase, we can also inhibit the overhydrogenation of butadiene to butane. And indeed, when we exposed our catalyst to the reaction mixture, we found that it was fairly selective for the formation of transbutene. And more importantly, we didn't have a lot of butane formation. And you will see in a moment, I'll give some results from the literature in which there was a much higher concentration of butane that is formed. So for us, it's just about 10% that is still considered fairly selective. So we also found that it was very highly active. And what's important is that, so this was probed for 4 hours, but there was absolutely no indication of deactivation. And previous results showed that in a matter of half an hour, catalyst already started to deactivate. So we did not notice anything like that. And we also carried out some extended X-ray absorption fine structure analysis, so which showed in operando conditions. And that told us that there is no obvious change of oxidation state of the palladium in the course of the reaction. But of course, this is not necessarily the best place to determine whether or not a hydride phase is formed. However, what we can tell that, for example, is there is no oxides formed or such things, but it seems that it's fairly stable from a chemical viewpoint as well. So there was a hypothesis in the literature that, as I mentioned, that the over-hydrogenation is a consequence of the formation of the beta hydride, also the interstitial hydride formation, which is more active than the metal, which and less selective than the metallic phase. So here is an example in which palladium particles were deposited on silica. So you can see that they're about 1.1 nanometer diameter on average, which is comparable with what we had in our system. And already you can see that they had over 50% of N-butane formed. Now in our case, that was only around 10%. So in our case, of course, when the hydride, when the palladium was confined in the part of the metal organic framework, this was to a much lesser extent. Now, the question is whether this hydride formation did not occur because the particles are simply too small or because they're not allowed to expand. So it has been previously suggested that in small particles as this, the hydride phase cannot form, but unfortunately in this case, the particles actually were larger than claimed in the manuscript. So in order to check whether or not the hydride phase really forms, we carried out some inelastic neutron scattering spectroscopy. Now, I really don't want to go into a lot of detail. A, this is not what I do on an everyday basis, and B, if I started to talk about this, I suppose it's just would never end. But suffice to say that, of course, neutrons are very sensitive to hydrogens, and to hydrogen in general, and the hydrogen atoms within the interstitial positions are very different spectroscopically from those that are the hydrogen molecule that is in the gas phase they're in equilibrium with, or even with the hydrogen atoms that are chemisorbed on the surface of the palladium catalyst. So we thought that we should be able to distinguish this and demonstrate its presence if it was formed. So what you have here in green, this is just obviously just a part of the neutron, the inelastic neutron scattering spectrum. So this is just the hydride phase. So this is just pure palladium under hydrogen pressure, minus the hydrogen, the gas phase, which actually comes at a very different energy range. So this is the peak we would be after. Now in black here you have a simulated spectrum, which is added up the framework itself and the palladium hydride to it. Well, it's a bit more complicated than that, but essentially this is the point. And in red, you have the actual experimental curve. And as you can see that we should be able to see this peak here corresponding to the beta hydride in case it formed. And as you can see, we don't see that. So this is one of the spectroscopies we carried out to show that there is no formation of hydride phase. And so with this, I would just like to, just quickly come back and show that indeed you could show that there is no hydride phase, and that is probably the reason of the particular catalytic properties, increased selectivity in particular of our system. And potentially this also may be the reason for the increased lifetime or robustness of the catalysis. Now, the other example I wanted to give is the use of metal organic frameworks as hydroxide ion conducting membranes. So this comes back to the hydrogen economy a little bit. I briefly mentioned it. I don't want to go into a lot of detail, but you would be aware that now there are commercially available hydrogen cars in which you would have a hydrogen tank. Now, whether or not it's just a compressed gas tank or an actual materials-based hydrogen storage system is actually irrelevant at this point. What we were interested in this work is this part of the vehicle, so that is the fuel cell. So what it does is an electrochemical cell in which we can oxidize hydrogen in a controlled fashion electrochemically to water. So typically you would have a proton exchange membrane fuel cell in which what's happening is you have the anode on which the hydrogen is oxidized into protons. And in between the anode and the cathode, there is the electrolyte, which is also contains the membrane itself, and it's permeable to the protons, which can diffuse through the cathode compartment and react with the hydroxide ions that are being produced on the cathode side through the reduction of oxygen. Now, the issue is that, of course, so we need here a proton transport through this membrane, and that means that the pH will be very low. You would be, obviously, you know that means that this is a highly corrosive environment. So, of course, that means that our electrodes and electrocatalysts need to be so robust as to survive in these highly acidic media. And which means that in practice that you need to use platinum, which is of course a very costly electrocatalyst, and it's becoming increasingly scarce as well. So there is an alternative, of course. Some other metals such as iron or nickel are quite as good electrocatalysts when it comes to, for example, hydrogen oxidation or oxygen reduction. However, of course, they're not stable in acidic media. So if we could go from acidic media to alkaline media, that would be a great advantage in terms of cost and sustainability of the fuel cell systems. So this is just to demonstrate a little bit how it works. And you still have obviously the same electrode reactions on both sides. What would be different is the electrolyte and the membrane in between. So instead of the protons going from the anode to the cathode, you would have hydroxide ions migrating from the cathode to the anode side, where the hydroxide ions can react with the oxidized hydrogen. And although this concept has been around for quite a lot of time, the bottleneck still remains the membrane itself. For proton exchange membrane fuel cells, of course, we have Nafion, which is very reliable, it's upscalable, and it's got very high proton conductivity, even though it's not particularly cheap. But such benchmark material does not exist for hydroxide ion conductive membranes. So this is what we thought that perhaps metal organic frameworks may be interesting for. There are a few hoops to overcome to make them stable under the conditions. Of course, we need to make them hydroxide ion conductors, and also to manufacture them and process them in a shape that is that lends itself to membrane applications. And of course, metal organic frameworks, being very highly crystalline, are typically very rigid. So in order to overcome the mechanical issues, what we did is we used electrospinning to process the metal organic frameworks in the forms of fiber mat. Now, the way to do that is we prepare a polymer solution, and this is, so first just do that the metal organic framework, and we can accelerate it onto a collector, and as the solvent evaporates, the polymer will be drawn into fibers, sort of intertwined fibers that form a highly intercalated matte structure. Now, when we mixed this with metal organic framework crystallite, we hypothesized that it is possible perhaps that as the polymer fibers are being drawn, they would be coated with the metal organic framework. So that was step one, and I will show you the results in just a second. But what I wanted to show is also that, of course, we wanted to demonstrate that this can still lend itself into highly hydroxide ion conducting materials. Now so for that we used a previous work in which they worked in the bulk, so powdered metal organic framework. But what they did is they used this zinc-based metal organic framework called ZIF8. Now what I would like you to focus on is that little grey dot there, which is a methyl group on the methylimidazole linker of the framework. Now this is obviously a charge neutral framework, and what they did is to make it intrinsically hydroxide ion conducting is to graft an ionic liquid on it whose anions were hydroxide ions. So the cation is the tetrabutyl ammonium ion, which can form hydrophobic interactions with the methyl group here. And as you manage to graft the cation on the framework, essentially make the framework positively charged if you wish, you can bring in the hydroxide ions into the pores, which are ideally loosely bonded mobile ions, which will in turn endow the framework with hydroxide ion conductivity. I should say that they did improve the conductivity, but still it was a relatively low conductivity. But we thought it was a good system, model system for us with which we can work and see if we can make the process membrane out of it. And so first and foremost, of course, we managed to do it, and that is what's shown here. So here you can see the scanning electron micrograph of just the pure polymer without framework on it. And as we mix the polymer solution with the framework crystallites, we get to this sample. And as you can see, particularly maybe the best giveaway is this high charging you get from the non-conducting or insulating framework, is that actually we really managed to very intimately coat the fibers with metal organic frameworks. And furthermore, you can take this fiber mat and immerse into a metal organic framework reagent solution and carry out the morph formation, and that can really fill the space in between the fibers with metal organic frameworks. So we can really control the density and the tightness of these membranes. And not only that, I'm not sure if this works, but we can also, okay. Sorry, this is not working. I tried it previously and it did work, but well, anyway, so you're just going to have to take my word for it. This is very flexible. Okay, so this is the research system just folding it and unfolding it, and it remains exactly the same. The other thing is that you can see that it's quite a large area. She's got quite small hands, but at the same time, it's still 15 centimeters in diameter. And that is solely determined by the target size of the electrospinning. So this is a really upscalable method as well. So yeah, you can control a lot of things: membrane, morphology, tightness, and density. And so in the second step, we added...
Petra, sorry to interrupt you. We are running a little bit out of time.
Oh,
so
okay.
Yes,
okay.
you could,
right, I'm gonna
slowly wrap it up. Yeah, thank you.
No problem. Sorry about that. So of course we looked at the whether or not we can graft this the ionic liquid on it, and we also demonstrated that the framework crystallinity is retained while also retaining some good mechanical properties. And I suppose the most important thing is that the hydroxide ion conductivity itself. So we got actually over 100 times improvement with respect to the powder material. And at room temperature, this is at the moment is a record-breaking hydroxide ion conductivity for metal organic frameworks, at least. In fact, by about an order of magnitude. So we're quite proud of it. And it's also a higher hydroxide ion conductivity at room temperature that is known for Nafion. And of course, this is a not very optimized synthesis. And just very briefly, I wanted to go through this. I'm not going to give any details. You can ask questions, but just to show, to come back that again, ideally, what you would want is to have these frameworks that are obtained in a sustainable fashion. And we have started to work on it. So I had a project student who carried out a method to make this UIO66 topology from in a hydrothermal synthesis. And this is important because it's one of the most used metal organic framework topology. However, you typically would synthesize in BMF in harsh conditions. And what we found is what's very crucial for this framework to assemble is that in the precursor solution, we have to make this hexanuclear zirconium complex, which can form this inorganic node and then allow for the assembly of the framework. So since then, we looked at other modulators. So here we looked at acetic acid. We also managed to show that you can use starch or, well, starch-derived compounds for it. So again, maybe starch-based could be used. And finally, and again, that's unfortunately, I don't have a lot of time for it, but with many of the metal organic frameworks using terephthalic acid as a linker, polyethylene terephthalate or PET plastic is one of the interesting linker sources that could be used. Now, this has been coined a while ago, but I would just like to point out that in this case, of course, you have aluminum chloride, in which the inorganic node is just the cation. So it's very easy, well, relatively easy to use just single cations as inorganic nodes for the assembly of framework in a sustainable way, because of course you don't have to worry about assembling polynuclear species. In the case of when we want to make this UIO topology out of it, previously it's been shown that you can only do it in organic solvents. And recently I've had a project student who also, well, at the end I ended up doing this because of COVID, but we managed to show that we can use PET plastic as a precursor, and in a one-pot mechanism we can convert it into the UIO structure. And while at the same time functionalizing the linker. And this is just to show that the UIO structure is formed. So just to conclude, in order to shift the energy paradigm, of course, we need advanced materials. And however, in order to really address the materials issues as well and waste challenges, these materials have to be developed sustainably. And I hope that I gave a little flavor of how metal organic frameworks can be interesting materials for both of these purposes, or from both of these aspects. And I gave an example of metal organic frameworks as template and supports for active and selective catalysts. So of course, they can be tuned for industrially relevant catalytic reactions, but what I'm quite interested in is it's because of their properties, but because of the properties of metal organic frameworks, in particular of their pores being so well determined in shape and size and in chemistry. They also can offer a unique opportunity for fundamental studies, such as, for example, distinguishing the catalytic properties of the methodic and the hydride phase of palladium. And I've also given an example of the application of meta-organic frameworks as ion exchange membranes, and show that they can be processed in, again, industrially interesting ways. So with that, I would just like to thank those the collaborators and those who were involved, and particularly, of course, all the students and the postdocs that were included. And yeah, so this is my latest group, and at Christmas too, and who would have thought that that was going to be the last picture we can take for quite some time, and the funders as well. And I was looking through my photos from the Delft Times, and I thought this would be a nice proof that I have been there. So this is my bicycle, as you can see, with the Delft saddle cover as well. So I'd like to thank you for your attention with this, and I'm really looking forward to hearing some questions. And apologies if I've taken too long.